Right, so I will be recording this video as usual. Okay, so in event that there are some connection problem for students who are not able to access right now, they can actually refer to the video. Okay, just to let you know. Okay, so at any point of time, do stop me if you have any question, or you can always type in the chat panel, but it's harder for me to see from the chat panel. All right, so let's get started. Okay, so today we are looking at control again. This is already, we have already gone through that in the last two lectures. But today we're going to very quickly look at, or rather a quick revision on modeling second order system. And then this control of a second order system. So eventually it will lead us to how it is related to our robot joint control. So remember we talked about robot joint control earlier on, right? Okay. Okay. So we are right now at feedback control for linear system. Okay, so we did a very quick overview, and in last lecture we also look at independent joint control, how we can actually consider an entire manipulator arm as one that is consists of many different joints. And each joint can be looked at as a control system where we design the control law or control scheme to eventually control the entire manipulator arm. All right. So later this week, on Thursday, we're going to move on to non-linear system and take a look at force control as well, a little bit of it. Okay. So that is the plan. Then we will have completed this dynamics and control. Okay. So very quick announcement. Midterm test is supposed to be scheduled this Thursday, but we're going to push it to next Thursday. We postpone it to next Thursday. And hopefully by then we are able to be back in person to do the test. If not, we will arrange for some online approach in doing the midterm. All right, so it is going to be on April 21st. Okay, we're not going to postpone it anymore. Okay, if we can't do it in person, then we will have to do it online. All right, and you will be tested on material up to robot dynamics. So this will actually include spatial representation, okay, your kinematics, all right, and of course, including product of exponential, okay, that includes your forward and inverse kinematics, and also robot dynamics. Okay, so of course I will put out more detail this information sheet. Okay, and there won't be any lab this week. Okay, because we are not able to do any in-person lab, right? And homework 4 is available, so please take a look at it. Okay, so last lecture, like what I mentioned, we look at an overview of robot control, right? So this is actually last week material. We actually look at the overview of robot control, and then we talk about feedback control. Okay, essentially we are going to use feedback control for our robot control. Most of the time when we don't have exact knowledge of the system, okay, and we're going to expect some disturbance and a lot of uncertainty. So feedback control is something that is required in most practical case. And we look at joint control, which is where we just isolate each of these individual joint as a single control system to make sure that we can achieve what we require for just that joint itself. Okay, and from that joint control, we look at the various components, which is actually the subject of mechatronics, where you look at the actuator, the motor, sensor, and transmission mechanism, like the gearbox and the pulley belt system, etc. Okay, so today we're going to recap second order system. All right, so if you still remember, okay, if we are looking at a manipulator arm, for example, okay, so usually a control problem is such that we are interested in achieving certain outcome. And how do we actually achieve that outcome? We need to know what kind of input to send to the system. All right. So in a case, most of the time, let's say we are going to control the motion of this thing. Okay. X dot. Okay. We want to control something like this. We need to know the kind of force that we can input to it. And so in the case of a manipulator arm, one practical way of seeing this is that we can just look at one individual joint, say tau 1, and then we will go about making sure that, let me change this, that we can achieve the right desired theta and theta dot. All right. So we want to do something like that. And so we look at this as just one single joint. So this is just independent joint. Okay. Now, so in this lecture, we're going to model and we're going to look at modeling and control of second order system. Okay. And we will relate it to joint control. Okay, so there are various type of robot control scheme that we are going to look at, not just joint control. Okay, but we will do this after that. Okay, not just all right. So there are also other control scheme for manipulator. All right. Maybe. Okay, so that's the idea. All right. So the central question in designing a control system, I'm sure many of you who have gone through control theory or related topic in control system, you probably know that it is important for us to be able to specify the system response, okay, of this particular system that we are controlling. So in that control system, we can look at it as a dynamic system where we get to tune certain parameters, okay, and we want to make sure that the system behave in a certain way, okay, and so that is by specifying the system response. And so no matter the first priority, of course, is to ensure stability of that system. Okay, so it doesn't really matter if you are if you don't achieve stability, okay, the control will be meaningless. Okay, meaning because you can't actually make sure that you will eventually get to the desired outcome that you want. Okay, it can at any point of time move away from the desired outcome. All right. So think of it as this way: when you have this dynamic system. Okay, so a lot of time, say if you are a designer of this dynamic system, okay, so this is a dynamic system. Say the equation could be F equal to W dot plus BX dot plus KX. Okay, so of course, say if we are looking at the free response, okay, you can of course design this system, okay, with the right B and K. You can design it with the right B and the right K. So as a designer, you may be able to change the parameters like the damping coefficient, the stiffness of the entire system. Say, imagine if you have like a vehicle, okay, so you have a car, okay, moving on a bumpy road. And this car, of course, you want to design some suspension system, okay? So when the car is traveling on this road here, sometimes there are some bumps here, okay? It will actually make the car, um, uh, make the passenger in the car uncomfortable when there's this kind of bumpy vibration. So you want to be able to design, say, a large B so that it will actually damp up this sudden bump. Okay, so you can actually design this B. But once you design it, you can't really change it. This dynamic system will have this parameter already fixed. Okay, so even though as a designer you may be able to change, choose the right combination of B and K, but you can't really change it at any point of time during the operation. Okay, so one way is, of course, if you design a controller here, okay, you're going to put in some gain, any kind of K in this controller, okay, such that you can change the entire system, change the entire dynamic of the system. Okay, so now this entire system become another dynamic system. But this time round, you can have this K change accordingly. Okay, so you may not be able to change what is already inbuilt in this original dynamic system, but by designing a controller, you can actually change it. And so this allow you to change the system response, okay, how the system should behave accordingly. Okay, and stability analysis will actually take a very quick look at it when we talk about this second order system. All right. Of course, you can send in the right kind of view, okay, to produce the state of the system. All right. Okay, so now let's move on to modeling of second order system. And this is not something new to most of you. Okay, so take it as a very quick recap to put us all in the same page for the context of robot applications. Okay, so if we are looking at a second order system like this, okay, the first thing we can do is to work out the equation of motion, right? In this case, if you look at this, say there's no external force, okay, so in this case, we are not looking at any external force. Right? So it should be quite straightforward that is if you actually have a displacement, a slight displacement, and so you will have your force from the spring. Okay, you will also have the force from the damper. Okay, and it's going to be ma, the resultant force. Right, it's going to be equal to ma. And if you decide to draw a free body diagram, it really says that you will have two forces acting on it. Okay, one is your Fs and Ft. All right, and so of course this will be kx, okay, plus, and this b is proportional to the speed, okay, or the velocity at which the body is moving. All right, it's going to be acceleration is nothing but sorry, because your arrow is actually pulling the body here will be positive, right? Okay, so this side here is positive, right? So you will actually need to put a negative sign here. Okay, so if we bring all of them to the same side, will be all right. So that is when we have no external force. Okay, that's when we have no external force. Okay, so the idea is the same. We work out this equation of motion. All right. So when you have, make sure that you are careful about the sign. But of course, this is quite straightforward. This is quite obvious in this case when you have multiple body. All right, you have various body connected together, which is a multi-body dynamic system. You're gonna be slightly more careful with the sign that you have. And if you recall how we can change it into S domain, right? S domain is when you do a Laplace transform. Okay, so if you consider the initial value to be 0, right? So in this case, we actually put in the initial value, all right? But a lot of time, initial value can be put as 0, okay? Unless stated otherwise in the question, right? So in this case, you're going to do Laplace transform from here. You take Laplace transform. Okay, you take Laplace transform. and you get something like this. Okay, basically, initial condition is when t equal to 0. Okay, what is your x and x dot? So we denote this as this. Okay. So the initial displacement and the initial velocity. All right. And so from here, you can make this x the subject of formula. Because eventually what we want is the system response, okay, which is eventually we're going to kind of find a solution for the differential equation, right? You want to know what this is. Okay, so one way, of course, you can work out in this S domain where you solve it and then do an inverse Laplace to change it back to the time domain, right? But from here, even just by looking at this here, we can already uh, establish some information about this system by writing down the characteristic equation. All right. Okay, so in this case, it's a free response system. Okay. This is because when there's no external force to it, okay, you're going to have homogeneous equation if you still recall that. But if you don't recall that, it's fine. Just follow through this and look at some of this important property when we are talking about this second order system. Okay, we're going to use this mass spring damper system as an example to slowly build out our explanation. Okay, but of course, it will not always be that simple. Okay, so we want to find the characteristic equation if we solve for the root that is actually giving us the pole of the transfer function. If you look carefully here, okay, if we have this becoming 0, okay, this part here, if this part becomes 0, we are actually getting the pole. Okay, so we call this the characteristic equation. Right. So from here, if we use the quadratic formula, we can very quickly get the two pole here, right? And from here, by looking at the determinant here, right, we can already have some information about the system. All right. So imagine if you're going to have this part being positive, okay? If this part is positive, meaning you will have real and unequal root, okay? Because it's not going to be no imaginary number is involved in this case. Of course, if you square root something negative, then you will have to start to worry about complex root, right? Because there will be I involved, okay, when you square root -1. All right, so in this case, in a case of overdamp, where this part here, b squared minus 4mk, is greater than 0, okay, that will be overdamp, a situation of overdamp where you have real and unequal roots. Okay, in the case where it is negative or like what I mentioned earlier on, okay, you're going to expect imaginary number, okay, because you're going to have, when you try to square root negative number, you're going to have imaginary number, and that will give you complex roots, right? And in this case, this is actually under that, right? When you have this I here, it kind of means that you will have oscillating component, right? Okay, so these are concepts that you should feel comfortable with. Maybe you may not remember the detail, but you should try to be comfortable with concept like this. So when you have this imaginary number, it's it's kind of like you're actually seeing some oscillation involved in this case. And when this part here is equal to 0, we are going to see this real and equal root, right? Because this your part here, your term here will actually be equal to 0. Okay, if this is equal to 0, it will be equal to 0. All right, and so as in this case, S1 and S2 are going to be the same. Okay, they are both going to be the same. Okay, because it's plus or minus 0 on this side. All right, so that is just by looking at this characteristic equation, we can already see whether the system is over damped, under damped, or critically damped. Okay. Okay, so now, of course, we are interested in the system response, which is the general solution, right? Eventually, we want to be able to write out what is this thing, right? Yeah, interested in finding out this. Okay. So let's look at a case of overdamped system where this b squared minus 4mk is greater than 0. Okay, this is where you will not have any this complex imaginary term. Okay, you're gonna have real and unequal root, right? So in this case, your solution to this homogeneous equation, homogeneous second order equation, is actually in the form of this xt equal to c1 e to the power of s1 t plus c2 e to the power of s2 t, right? So remember your s1 and s2, okay, they are the pole. Okay, so this will be the equation form. And when you are looking at something that is that involve your imaginary number as well, or a complex root for your characteristic equation, your form of this differential equation will actually be with the cosine and sine term as well. Okay, so the term will involve cosine and sine, right? And in the case of critically damped, okay, it will be in this form. Okay, right. So these are initial value problem. Okay, this IVP, we call it IVP, initial value problem, allow you to solve for your C1, C2 if you know the initial conditions. Okay, so this is a case where you are given so that should be there. All right. So I guess this part is not something new. Most of you will already know about. So let's take a look at some example, okay, very quickly. So to make sure that we recall all this that we have learned, right? So say in this case, again, the same example, we have this block of mass M, and then we are going to plug in value. Just now we actually give a general form. We have the characteristic equation was ms squared plus bs plus k, right? So remember our characteristic equation. Okay, k equal to 0. right? Okay, so in this case, of course, we are now given a few information. Okay, first we have our M, we have our B, and we have our K. We have our dynamic parameters of this system, and we also have the initial condition. Okay, this is x0 equal to -1. All right, so now start by plugging in our M equal to 1, B equal to 5, K equal to 6. All right, so we're gonna different colors. Okay, so we plug in our value, this one, right? And so in this case, when we solve for the root of our characteristic equation, we have S1 equal to -2, S2 equal to -3. And with this real and equal root, we know that it is under them. Sorry, it is over them. All right. In this case, it is over them, and so we have this system response in the form of this solution, right? And so we substitute S1 to be -2, S2 equal to -3. Okay, so what is left now is to solve for C1 and C2. Okay, okay, at rest, maybe I should. This part here at rest means that your initial velocity equal to 0. Okay, at rest. That means initially it's not moving with velocity. It was being pulled. Okay, you pull it to -1 and then you release it and it will start to move over time. Okay, so now you put in this two value, this initial condition. Okay, you put in the initial condition. All right. And to satisfy the initial condition, your C1 and C2, okay, C1 and C2 will have to be -3 and 2. And so now your solution, right? So this is for the case of over there. Okay. All right, so under them, the same thing. So I'm gonna go slightly faster. Okay, just now we actually, I actually guide you step by step, plugging in all the number, and now this will be the same thing, except that of course you won't know it's under them until you work out a characteristic equation and you realize that your b squared minus 4mk, okay, is actually smaller than 0, okay? And because of that, your complex root, right, is going to involve imaginary number is a yeah, of course, it's a complex root, or rather it's a pair of conjugate complex roots, right? So your system response will have this form where you have your cosine and sine, right? And now you do the same thing, substitute this initial displacement -1, initial velocity 0, and you solve for C1, C2, okay? You will have this solution here. Okay, the C1 and C2 that satisfy your initial condition can be plugged in to your solution form to get the actual solution. So in your this is in your S in the S domain, okay, and time domain. Enough space for that. All right. All right. So in S domain, it is quite straightforward. Okay. You can see that in this complex plane, when you put out you plot out these two root of your characteristic equation, you will see that whenever it is on the left side of the plane, okay, the left half side, it will actually be stable. Okay, in all natural system where you don't have anything, when it go through a free response, it's going to be stable, right? If you don't put in a controller that is not well designed, because naturally there will be dissipation of energy to eventually bring the system to stability. All right, so whenever you have something like this, it will be on the left half plane. Okay. So just now, we have two distinct routes. Earlier on, we have in our previous example. All right, take a look at our previous example. Right, we have two distinct routes here. So they are on the horizontal axis. Okay, it's not. It doesn't involve any imaginary number. It's just real root. Right. So in this case, we have complex root. Okay, so I will not go too much into this detail. All right, but the idea here is quite common to all other problem of solving this form of differential equation. All right, and so if we look at the situation of under dam, okay, you will see that it is actually going to be oscillating. There will be oscillating component, and at the same time, it will also decay. Right. So this is kind of like your exponential component. All right. And so you also have cyclical, is periodic and cyclical component. Okay. So it's the oscillating component. All right. So critically damped will be the case where we have equal root. Okay, so S1 and S2, they are the same. All right, because our b square minus 4mk equal to 0. Okay, so in other words, we have b square minus 4mk equal to 0. Okay, which means that b equal to okay, maybe I should take shortcut. B square equal to 4 a. All right. So this is a situation where you have your critically damped response, okay, where the system is critically damped, right? The same thing, just changing the form of your solution. In this case, solve for your C1 and C2 that satisfy the initial condition, okay, to eventually arrive at your system response. Okay, so for the motion that is starting from t equal to 0, okay, all the way where your t slowly increase, you will have a signal of xt that looks something like this. -1, -2, t. Sorry, this part here is a little bit hard for me to write when my camera is on the screen, because I tend to like push the screen. Okay, so let's see. When we look at this example, 8.2 to 8.4, actually they are in your textbook, example 9 point something. I can't remember. Yeah, it is. It should be in chapter 9, so example 9.2, and so on. Okay. So of course, all these systems are stable, like what I mentioned earlier on. The natural system will tend to stability because your B is greater than 0. Right? It kind of says that the energy will actually be dissipated and slowly. I mean, in ideal case, a spring will actually stop eventually, okay, because of the drag force and everything. Even if you bring it up to the space, okay, where there's no air resistance or anything, it is still likely to come to a stop one day, okay, because the material itself will have hysteresis. It will actually dissipate energy, right? So most of the time, you are seeing systems that are stable with our MBK greater than 0. Okay, so these are, of course, natural response. All right, in free oscillation, the system will have natural response. In control application, remember this time round, we are not really just looking at a natural system. Okay? If we have a system, but we actually put in something extra. Okay, we actually put in a controller now to send this system. And so this entire thing now, okay, this entire thing, of course, is it can also be viewed as a system. Okay, this is now a new system, and it may not always be stable. Okay, if you don't design a controller correctly, it can actually lead to instability. Right, that's why we need to do stability analysis. Okay. All right, so what we saw earlier on, okay, this part here being equal to 0, okay, means that is free response. All right, and of course, in this case, okay, or sometimes we call this natural response. Okay, when you don't do anything to it, no external force, okay, no external. All right, and you will have a natural frequency where this thing will just oscillate by itself at this natural frequency, okay, square root k over m, right? And our damping ratio, okay, if you still remember, right, just now when we say that our B is going to be equal to square root, okay, that is when it is critically damped. Right? And so we can work out the damping ratio. So if our this damping ratio is equal to this value, it will actually be critically damped. Okay, so this is all right. So in free response, we already just now we already did this. Okay, just to summarize. Of course, just now we were looking at this v square minus 4mk to see whether it is greater than, smaller than, or equal to 0, right? We compare it with 0, okay? To see whether it's greater than, smaller than. And it turns out that we can just look at this damping ratio, okay? Eta in this case, right? When the damping ratio is greater than 1. Of course, just now when we were saying that it is equal to 1, right? It will be critically damped. Okay, so anything in between 0 to 1, it is under damped, right? When it is under damped, there will be oscillating, there will be a complex root, right? Meaning your imaginary term will exist. Okay, so you're going to see something that is oscillating, right? When it is over damped, of course, it will just be exponentially decaying, all right? And when there is no damping at all, damping equal to 0, okay, maybe we didn't really do this. Just now, I guess sometimes your S1 and S2 could end up here. Okay? That is when there is no damping, right? So this part here, in a way, it is conditionally stable. So depending on what kind of input you send into the system, okay, of course, free response, it will just be a sinusoidal function, okay? If you look at this, this is really a sinusoidal function, right? But let's say if you send in a RAM input, of course, it's going to make it unstable, okay? For an obvious example. All right. So if we recall designing control, what we really want to achieve, we want to be able to specify the system behavior. But of course, what kind of system behavior do we want to specify? And most of you probably know that we can specify things like the steady state error, the rise time, okay, the overshoot settling time, all right? And eventually, or ultimately, we need to consider stability. We need to make sure that it is stable. No matter how well this system perform, happen to kind of you think that it will have very low overshoot or things like that. But if you don't guarantee stability, it's not meaningful at all. All right. So just a very quick visualization. Of course, it depends on what kind of response that you are looking at. In this case, it's kind of like a step response. Okay, you have a step response of the system. All right. So you want to see some of this performance. like your rise time, it is actually a time from 10%, okay, to 90% when you compare to this steady state, right? This is a steady state. All right. And then overshoot kind of measure this thing here. It's overshoot. All right. And settling time. Settling. Okay. So it's actually the first time from the transient to decay to within a small percentage of y infinity. And sometimes we denote this like 5% times 5%. Okay. It could be 3%, it could be 5%. Okay. So first we answer the central question as we posted earlier. Right. So how is this modeling of the second order system and the ability to specify the system response related to control? So we're going to look at control of our second order system. Okay. Early on, we already see our modeling of the dynamic of the second order system. Okay. So this is just when we are applying force. Okay. Remember that in this free oscillation, okay, just now it was a free response, okay, or natural response. Free response. Okay, when we have free oscillation. So in control application, you're gonna have force that is driving the system. So it's a force response. So this time around, your left-hand side of your equation, or rather it's no longer homogeneous equation, you will have external force, right? Okay. So when you draw the free body diagram this time around, okay, you will have external force. All right. So no longer homogeneous equation. We are looking at non-homogeneous ODE, and force response will actually be a combination of our free response and a particular solution, right? So we are actually looking at the, in other words, the transient and the steady state. Okay, that will be a transient part and the steady state part. Okay, but mathematically, this is just the solution of our ODE with the homogeneous. Yeah, the Americans don't spell it with E, and a particular solution, right? Okay, so these are of course important control applications. So for human being, of course, when you contact something that is like having some properties of stiffness and damping coefficient, okay, we naturally know how to adjust to it. But when you want a robot to do something like that, okay, when it is interacting with the environment, okay, when a robot interacts with the environment, okay, you will need to be able to model it in such a way that it can actually satisfy some of your performance requirement. Okay, control performance requirement. Let me just make sure that I'm on time. Okay. So again, we look at this system here, and one good way of representing it, of course, is to use block diagram. And later on, when we represent our various control scheme, we will be looking at block diagram as well. Okay, so I hope this is not unfamiliar to you. Okay, in this case, this is actually in the time domain. All right, so basically, this system itself, okay, is this is like the plant. Okay, if you look at it, it's like a plant. Okay, so this is how the robot, how this mass will behave. But of course, you can have a robot. Okay, so you can actually attach a robot, okay, to this thing. To draw it out to the force. Okay, so the robot can actually apply a force to further control the outcome of this motion, right? The motion of this M here. Sorry, I missed on this. Okay, so this is actually a time domain. Right? So you can also do a Laplace transform, right? So double zero initial value, that means this will be, both of them will be zero, okay? Your initial velocity and your initial speed will be zero, right? Assuming that this thing doesn't really move, but when you start to have a force to move it, okay, you can say a robot moving this mass, it will actually be in this represented by this equation in the S domain. Okay, so S domain integration will just be 1 over S. Right? And so, of course, you can find a transfer function. Okay, if now you have this as the input, right? Transfer function is a ratio of the output over input in this S domain, right? Of course, in signal processing, it is just the convolution with the impulse response. Okay. Oh, sorry, the Laplace transform of the impulse response. All right. So anyway, working on this transfer function is just taking your x out, okay, and then bringing all this term to one side. Okay, so in a way you kind of okay, and then here you work out your transfer function. So this is your transfer function. So instead of writing this entire plan here, instead of writing this, it's this way. All right, it's equivalent. Okay, so remember, if we are talking about open loop, this was a plant, say the 1 over mx squared plus b plus k, for example, all right? And so you're going to send in something that will give you the desired state, right? So you will design a controller that will send in something to the plant, such that the actual and the desired state will be very close, right? So of course, through pre-established model, you can generate that command without any feedback. All right. So that is open loop system. Or you can control the robot to maintain this desired state, where you feedback the measurement to produce this command that will minimize the error, right? So this is actually your closed loop system, right? Closed loop system. All right. So now, if say we have this robot here and we have certain input, we have the ability to send some inputs here. If we can actually put in input that will, of course, result in a force, right? And eventually the dynamic equation will look like this time around. All right. And so we're going to write this in, or rather represent this in a block diagram form. Okay. But first, we want to design this servo law or a control law, right? So we see that we need to so-called input this FT into the system. We need to know the kind of FT to input to the system. Okay. So let's say we design a control law that will tell us what kind of FT to put in by observing the X and X dot. Okay. So by being able to feedback our X and X dot, that means if we have sensor or something like that, we can get our X and we can get our X dot. Okay. That will be feedback with this KP and KV. All right. So now we set our FT, okay, our F to be equal to the feedback in proportion of KP and KV. Okay. So remember the dynamic equation is really mx double dot plus bx dot plus k equal to f. All right. Maybe I will use a different color. So now we substitute this f in. All right. It's fine. Okay. And so if we rearrange it such that we look at the homogeneous equation, now we're going to our mx double dot plus this is actually b minus kv, right? We arrange all our x dot term and x term together, okay? And so this is plus k minus kp, right? So that is what we can expect. Let's see if I can. All right. Okay, so now we have our closed loop stiffness and our closed loop damping. Okay, so these are all your closed loop parameters. All right. So this is your closed loop stiffness. Okay, so again, let's plug in some values so that we can see how this go. Right. So we look at the same example again with m equal to 1, b equal to 1, k equal to 1, and initial displacement -1 again. So at rest, meaning x dot 0 equal to 0. All right. So initially your x dot 0 equal to 0. Okay, and this part here is actually x 0. Okay. And so what is now the closed loop stiffness damping? Right. We know that if we want to have our closed loop stiffness of 16, okay, and a few information that we need to take note, okay. So one is the critically damped, okay. So it is, we're talking about closed loop stiffness of 16 and critically damped, all right. So closed loop stiffness equal to 16. All right, remember this K prime, our closed loop stiffness is actually K minus Kp, right? If we see what we work out here, sorry, K plus Kp. And this is a minus sign here, you bring over. All right. Yeah, previously I made a mistake in the writing as well. All right. So it's K plus Kp, where we want to get 16. And so it will be 16 minus 1, right? Because K is equal to 1. And so our K prime equal to 16, okay, k plus kp, so kp is equal to 15, right? Okay, and to find our critically damped response for this b prime, okay, the closed loop damping, okay, we need to use the condition for critically damped. Okay, remember you're gonna have this b equal to 2 square root mk, right? All right, so now you can solve for your b prime as well, okay, with your mk. And then with that, you can solve for your kv, and that will give you your control gain. All right. So basically here what you do is just substituting, right? Because you have your kp equal to 15, right? Okay. So this should actually be example 8. So previously when we do without controller, right? Say we give an initial displacement of -1, and remember x0 equal to -1. Okay, the system will actually behave like the red dotted line, right? But now that we put in our kp and kv, okay, after putting kp, kv, we're going to have a critically damped system that recovers a lot better. Okay, so now you have a shorter settling time, you have less overshoot. Okay. Okay, so you will actually use your KP and KV to improve your system response performance, the performance of your system response. Okay, you actually lower the overshoot and you shorten the settling time. Okay, and so this last part here, I'm going to show you something that is probably not as common, but you will actually see why this is useful later on when we move on to this looking at non-linear system with non-linearities. Okay, this way of control partitioning approach. So instead of looking at the control system earlier on with just a single servo law, okay, so just now you remember we see this entire thing, this entire thing here as a system earlier on. Okay, now we're going to partition out the system. Say if we already know some of the value like M, B, and K, we can actually represent it slightly differently. Okay, so the model-based portion of our this control law, okay, will actually be given by this form here. So we actually separate one with the model and also the servo the servo portion. Here we have our model portion and we have our servo portion. Okay, so we actually have this two things. And so the model portion is when we see that this f equal to alpha f prime by plus this beta. Okay, so now we are actually writing it in this form. Okay, our model. So this equation here, we are going to split it into alpha f prime by plus b prime. Okay, so let's say if you substitute this into your equation. Okay, so this part here will just be alpha f prime by plus beta. All right, and so from here, of course, if you just split this part here, okay, this will be your beta, right? And alpha will be the inertia, the mass in this case. All right. So f prime will be x double dot. And so in your servo portion, the same as what we have earlier on. Okay, but this time round instead of f is f prime, right? So our servo portion, okay, you're gonna have maybe use a different color. Okay. So now combining this, okay, since our model portion actually make our x double dot equal to f prime, okay, so we can actually put this in, right, with our model portion. And so when we write it down in this block diagram, it should look something like this. Okay, where this part here, okay, you will have your servo part, right, where you send in this f prime. Maybe I should write the boundary here. So you actually send in this f prime here. Okay. So now you kind of already know your B, K, and M. So you can write it, or you can represent the system in this way. Okay. So again, let's plug in the same numbers in that same problem, but with different representation of our control scheme. So now we are using control law partitioning. All right. So instead, just now we don't know, we just treat the entire system as one big black box like system. So we didn't actually identify our M, B, and K, right? Just now. But now we kind of put this system and have our information about M, B, and K within that model, right? So let's see how is it different. Okay, so this time around will be the same. Effective system now, since we already put in our M inside the model base now, so we just need to write straight away the same thing, KP. Okay, if the closed loop system is 16, right? So it just basically means that 16, right? Because now your closed loop system, you're looking at this thing, this entire servo law. Okay. So the same thing, if you want it to be critically damped, right? You can work out your KV as well, right? So it's probably 2 times 8. Oh, sorry. Yes. Your KP is 16, right? So 4 should be 4. Square root of 16 is 4. Okay. So now you have this control partitioning law. Okay. All right, so I'm going to end this quite soon. Okay, just to relate it to two very important applications. Okay, so you're going to have, say in robot application, what you really want to do is to make the robot move in a specific trajectory that you assign. So we haven't do planning, but trajectory is basically the path with time profile, okay, along the time. So it's actually changing along the time. Okay, so it's not just geometrical. Okay, so you want the body to move in a specific way. Okay, you want to specify the motion. And so this is, sorry. Okay, trajectory following. You want to specify the motion. All right. So here, this is actually a form of position regulation. Okay, where we want to maintain the block at desired position. So the equilibrium to be at 0. So we don't want it to be disturbed. Okay, we want to make sure that it's always at this 0. So when we specify it, it will not have any deviation from the equilibrium position. So more generally, we can actually specify this desired motion trajectory to be followed, right? So now we are looking at this force response where we have a controller to tell us what kind of force to send in to do this trajectory following. Okay. So here we apply the same thing, but we want to minimize the error, remember? So if we have a desired profile, say we have desired displacement XD, okay, XD minus X is going to be the error. So we want, this is a desired x value, we want it to be xd, but the actual value, okay, is going to be x. And so the error will of course be the difference, right? And we feedback this error with our control gain, right? So now we feedback this error and then we do it with our control gain. All right, and we can work out this servo control law, as in we already established this servo control law, and with the partitioning control law partitioning approach, we can now write it down in this form. And so if we look at the error, okay, this x double dot minus x double dot d give us e double dot, okay, and so we leave everything on our left hand side, okay. This e double dot is basically equal to this minus x d, okay, right? So that is basically the form, and that is how we can minimize the error when we do our trajectory following. The second application that is also important is disturbance rejection. So in event where there is something that disturbs the robot, to move it away from the equilibrium, are we able to reject this disturbance? So our servo law that we use, we implement two control gain, Kp and Kb. So think about it, is that actually enough? And most of you probably will already know the answer that it's not probably adequate, okay, in this case, right? For those who have done PID control before, right? You see that if we have a disturbance, okay, this time around, we introduce a disturbance, all right? We introduce this disturbance as this, okay? And even if we put very large Kp, our steady state error, okay, with this disturbance is just going to be divided. It's just going to be the disturbance divided by this Kp. So unless if we have infinity Kp, then we can have zero steady state error, which is not possible. We can reduce this steady state error by setting very, very large Kp, but it cannot really eliminate it, all right? We can't really eliminate it. So one way of doing this, of course, is to introduce another term, all right, where you integrate the error, okay, to your controller. So you now have this Ki term. So this is your proportional integral derivative control where we have PID. So now we actually need, we know that we actually need one integral term as well, right? So taking time derivative, if we consider the disturbance to be constant, okay, we're gonna, with this Ki gain, all right, we can actually achieve this zero steady state error eventually, all right? So next lecture, we're gonna come back, okay, in our next lecture, we're gonna come back to look at this modeling of a single joint, okay? How we can actually use what we have learned or what we have revised on second order system and control for second order system and relate it to our joint control, single joint control. And then we will move on to other form of control scheme and eventually non-linearities and force control. All right. Sorry, I'm actually a little bit over time, so I will stop here. Okay, so if you have any question, please feel free to ask. All right, I will stop the video.